What is a compound? You've learned about elements in the periodic table. An element is made up of only one type of atom, but many substances are made of more than one type of atom. When different atoms join tightly together through bonding, they form a compound. For example, when sodium atoms bond with chlorine atoms, they form sodium chloride, common table salt. A compound has completely different properties from its original elements. You may have eaten sodium chloride today, but you wouldn't want to eat pure sodium or chlorine. Compounds have chemical names and formulas. The formula shows which elements are bonded together, like H2O for water or CO2 for carbon dioxide. Remember, if you see different types of atoms bonded together in a particle diagram, it's a compound. So compounds are everywhere around us, from the salt on your food to the water you drink. They're formed when different elements bond together to create something entirely new.
Science is all about communication, about sharing ideas and discoveries. Imagine trying to build something amazing, but everyone calls the pieces by a different name. It would be chaos, right? Well, chemistry is the same way. Every single substance in the universe, from the air we breathe to the salt on our fries, is made of tiny building blocks called atoms. When these atoms join together, they form compounds, and each one of these compounds needs a unique name. This isn't just to be tidy. It's so a scientist in Tokyo can understand a scientist in Toronto perfectly. A chemical name is like a secret code that isn't so secret. It tells you exactly what ingredients are inside a compound. Think of it like a recipe. The name of a dish, like chocolate chip cookie, tells you the key ingredients you can expect to find. Similarly, the chemical name sodium chloride instantly tells a chemist that the compound is made from two specific elements, sodium and chlorine. This system of naming, which we call nomenclature, is a universal language. It allows us to write down, talk about, and understand the millions of different substances that make up our world without any confusion. It's a powerful tool that turns a jumble of letters and symbols into precise information, ensuring that when we talk about a substance, we are all talking about the exact same thing. It's science in action, folks. One of the most common types of compounds forms when a metal teams up with a non-metal. The rule for naming these is wonderfully straightforward. First, you say the name of the metal element just as it is. No changes, no tricks. So, if your compound has sodium in it, you just start with the word sodium. If it has magnesium, you start with magnesium. This part is easy to remember because the metal gets to keep its original identity in the name. Next comes the non-metal, and this is where a small change happens. We take the name of the non-metal element and change its ending to ID. That's IDE. For example, the element chlorine becomes chloride. The element oxygen becomes oxide, and sulfur, you guessed it, it becomes sulfide. This ID ending is a huge clue. It tells you that the element is part of a simple two-element compound and that it's the non-metal partner in the relationship. Let's put it all together with the most famous example of all, table salt. The chemical formula for salt is NaCl. The Na is the symbol for the element sodium, which is a metal. The Cl is the symbol for the element chlorine, which is a non-metal. Following our rule, we take the metal's name first, sodium, then we take the non-metal, chlorine, and change its ending to ID, making it chloride. Put them together and what do you get? Sodium chloride, see? You just named a chemical compound. You didn't just memorize a name, you understood the logic behind it. That's the beauty of science. This rule works for countless other compounds. Take a compound made of magnesium and oxygen. The metal's name is magnesium. The non-metal oxygen becomes oxide, so the full name is magnesium oxide. How about a compound with lithium and fluorine? That would be lithium fluoride. The pattern is simple, predictable, and incredibly useful. The first word tells you the metal, and the second word with its ID ending tells you the non-metal. Now what about compounds made of two non-metals, like carbon and oxygen? Here things get even more interesting because these elements can combine in different ways to form different substances. For instance, carbon and oxygen can form the gas we breathe out, but they can also form a very dangerous poisonous gas. To tell them apart, we need to count the atoms. And to do that, we use special prefixes. These prefixes come from Greek and tell us exactly how many atoms of a particular element are in one molecule of the compound. It's like giving a head count for the atoms. Let's look at our first example. Carbon dioxide. The ID ending on oxide tells us it's made with oxygen. But what about that di at the beginning of oxide? Di is the Greek prefix for two, so dioxide means there are two oxygen atoms bonded to the carbon atom. The chemical formula for carbon dioxide is CO2. That little subscript 2 after the O confirms it. one carbon atom and two oxygen atoms. The name and the formula tell the exact same story, just in different languages. Now consider that other, more dangerous gas carbon monoxide. Here the prefix is mono, which means one. So monoxide tells us there is only one oxygen atom bonded to the carbon atom. Its chemical formula is CO. Notice there's no little number after the O. When there's no subscript, it's understood to mean there's just one atom. So carbon dioxide, CO2, and carbon monoxide, CO, are very different substances with very different properties, and their names, thanks to these prefixes, clearly reflect that critical difference. Other common prefixes include tri for 3 and tetra for 4. A chemical formula is the shorthand version of the name. It uses the 1 or 2 letter symbols for the elements from the periodic table, like C for carbon and O for oxygen. The small number written after and slightly below the symbol, the subscript, tells us the number of atoms of that element in the molecule. So for water, H2O, the formula tells us there are 2 hydrogen atoms, H, for every 1 oxygen atom, O. Sometimes the best way to understand the difference between elements and compounds is to draw them. Scientists use something called a particle diagram to do just that. Imagine you could zoom in and see the individual atoms or molecules. A particle diagram for an element would show only one type of atom, represented by identical circles. For example, a box full of pure helium would just be a bunch of separate, identical circles floating around. A box full of pure oxygen gas, O2, would show pairs of identical circles joined together, because oxygen atoms like to travel in twos. But in both cases, there's only one kind of atom present. A compound, on the other hand, is a substance where 2 or more different types of elements are chemically bonded together, so its particle diagram will show particles made of different circles joined together. A diagram for water, H2O, would show particles where 2 smaller circles, hydrogen, are stuck to one larger circle, oxygen. Every single particle in the box would look identical to the others, 2 hydrogens, 1 oxygen. The key difference is that an element has only one type of atom, while a compound has 2 or more types of atoms bonded into a single repeating unit. These diagrams make the abstract idea of atoms and molecules visible and much easier to grasp. Now, as you get into reading and writing chemical formulas, it's very important to be precise. The symbols for elements are sacred. A common mistake for beginners is mixing up symbols that look similar. For example, C is the symbol for carbon, but Ca is the symbol for a completely different element, calcium. One is a key component of life and fuels, the other is a metal that makes our bones strong. Likewise, Co is the symbol for the metal cobalt, but Co is the formula for the compound carbon monoxide. That capital O makes all the difference. Paying close attention to capitalization and letters is not just picky. It's essential for doing chemistry correctly and safely. So let's review our master plan for naming compounds. First, identify if you have a metal and a nonmetal or 2 nonmetals. For a metal and a nonmetal, state the metal's name and change the nonmetal's ending to ID, like in sodium chloride. For 2 nonmetals, use prefixes like mono and di to indicate the number of atoms of each element, such as in carbon dioxide. Always read chemical symbols carefully to avoid mix-ups between elements like carbon, C, and calcium, Ca. By following these rules, you can decode the language of chemistry and understand the ingredients that build our world. It's not magic, it's science, and it's awesome.